Hey there, and welcome back to the Sleepless Scientist. Tonight, we're embarking on a journey across time and ocean, pulled by an invisible force that shapes our world. We'll explore the ancient rhythms of our coasts and the quiet dance of the moon and the sea. It's a tale of discovery, patience, and the profound connection between Earth and sky. If you're ready to dive in, take a moment to hit that like button and subscribe so you don't miss any part of our exploration. Settle in, get comfortable, and let's begin. Our story begins not in a modern lab, but on the sun-baked shores of ancient civilizations. Imagine a world where the ocean was both provider and enigma, its daily breath a constant, powerful presence in human lives. For these early communities, the sea dictated rhythm. Fishing, gathering shellfish, safe passage for canoes all depended on understanding the water's ebb and flow. Life itself was tied to the shifting tide lines. Every sunrise brought a new observation. The water would creep up the sand, then retreat, sometimes far, sometimes less so. This daily change was a mystery, yet a predictable companion. What invisible hand pulled the ocean? What force compelled it to rise and fall with such regularity? This was the first great question posed by our ancestors, a puzzle whispered on the wind. They called it the ocean's breath or the heartbeat of the sea. It was a living entity, vast and powerful, with its own mysterious internal rhythm. This perception shaped their understanding of the world. Soon, a pattern began to emerge. As the sun set and the moon ascended, a subtle connection was noted. The tide seemed to mirror the lunar phases, a silent, celestial dance. The new moon, the full moon, these celestial markers coincided with the most dramatic tidal shifts. It wasn't a perfect one-to-one, but the correlation was too strong to ignore. Without instruments, they crafted mental maps passed down through generations. They learned to read the moon's face, associating its shape with the expected height of the water. This basic understanding was crucial for survival. Knowing when the fishing grounds would be accessible or when the river mouth would be deep enough for a boat meant the difference between plenty and scarcity. Yet the moon alone couldn't explain everything. Sometimes the tides were higher, sometimes lower, even under the same lunar phase. There were other factors at play, subtle and elusive. Perhaps the sun, too, played a role. Its immense presence in the sky, though less obviously linked than the moon, must surely exert some influence over the vast oceans. They observed the great tides, what we now call spring tides, occurring when the sun, moon, and earth aligned, and the small tides, neap tides, when they were at right angles. To explain these powerful, mysterious forces, myths were born. Gods and goddesses of the sea, colossal beasts, or spirits of the deep were said to control the ocean's rise and fall. One common belief was that a giant creature or deity breathed, and with each inhale, the ocean receded, and with each exhale, it surged back to shore. A simple, poetic explanation. While the myths provided comfort, practical needs demanded more precise understanding. Navigation, trade, and even warfare depended on knowing the tides. The earliest tide tables were not written but memorized. A series of observations, patterns, and rules of thumb passed from elder to apprentice, invaluable knowledge for coastal living. But the most perplexing mystery remained. Why did the ocean rise and fall twice a day? If the moon pulled the water towards it, why would there be a high tide on the opposite side of the earth? This wasn't a simple pull and release. There was a more complex mechanism at play, a hidden ballet of forces that eluded simple explanation for centuries. This deep, persistent mystery would eventually spark the earliest forms of scientific inquiry. Observation, hypothesis, and the relentless pursuit of understanding began to take root. The journey from attributing tides to deities to understanding them as a cosmic dance of gravity was a long one, spanning millennia. but it started with these first curious glances at the sea. The rhythm of the tides shaped not just the physical landscape, but the very culture and beliefs of coastal peoples. Their stories, their songs, their daily routines were all intertwined with the ocean's pulse. Through calm seas and stormy weather, the tides remained a constant, reliable companion, a force that could be harnessed if only its true nature could be deciphered. From the rocky coasts of the Mediterranean to the vast Pacific islands, the tidal phenomenon was universal. Every shore, every bay experienced this daily transformation. The moon, ever present in the night sky, became an object of reverence and scientific fascination. Its changing face was a clock, a calendar, and a key to the ocean's secrets. Even as the moon held sway, the sun's subtle influence could not be ignored. It was a secondary conductor in this grand orchestra, adding its own gravitational notes. Navigators faced immense challenges. Misjudging the tide could mean a ship grounded on a sandbar or unable to enter a vital port. Accuracy was a matter of life and death. The wisdom of elders gathered over lifetimes of observation became invaluable. Their collective knowledge formed the bedrock of early oceanography. The desire to unravel this mystery wasn't just academic, it was deeply practical, deeply human. It was about controlling one's destiny in the face of nature's might. This pull of the unknown, this urge to understand, is what drives all scientific discovery. It's the quiet hum in the background of human progress. From intuitive connections between the moon and the tides, humanity slowly began to build a logical framework. It was a slow, painstaking process, requiring immense patience. Though the concept of gravity was millennia away, these early observations were the first seeds. The understanding that something unseen was exerting a force across vast distances. The wonder of the tides was a shared human experience, a universal rhythm that connected diverse cultures across the globe, all gazing at the same moon, the same sea. Even with practical predictions, the fundamental why of the twice-daily tide continued to echo. It was a question that would challenge the brightest minds for centuries to come. This enduring mystery laid the groundwork for future scientific inquiry, setting the stage for brilliant thinkers to delve deeper into the mechanics of the cosmos. These ancient shores, with their rhythmic ebb and flow, represent the calm before the storm of knowledge, the quiet beginning of a profound scientific journey. From simple observation, the path would lead to complex theories, mathematical models, and eventually, a universal law that explained not just the tides, but the very fabric of the universe. As we leave these ancient observers, their questions linger. They invite us to continue our own exploration, to peer closer at the celestial mechanics that govern our world. Join us next time as we move beyond the shores of antiquity and begin to uncover the scientific breakthroughs that finally illuminated the hidden power of the moon's quiet pull. Until then, keep wondering. The ancient questions about the ocean's breath lingered, moving from the realm of myth to the emerging world of scientific inquiry. Minds began to seek mechanisms, not just metaphors, for the rhythms of the sea. The 17th century dawned, a time of profound intellectual awakening. Observatories were built and the heavens were scrutinized with new instruments. The Earth was no longer the static center, but a body in motion. Among the first to grapple with the tides scientifically was Galileo Galilei. His keen observations of the heavens had already reshaped our understanding of the cosmos. Galileo proposed a bold idea, though ultimately incorrect. He suggested the tides were a consequence of the Earth's rotation and its orbital motion around the sun. He envisioned the oceans like water sloshing in a moving vessel. As the Earth sped up and slowed down in its daily rotation, the water would surge and recede, he thought. It was an elegant concept rooted in the mechanics of motion, yet it struggled to explain the twice-daily rhythm or the precise timing of the high and low waters. The moon's undeniable influence, so clearly observed by ancient cultures, was largely absent from Galileo's model. The puzzle of the tides remained incomplete. A deeper, more fundamental force was needed to truly unlock the ocean's secret, a force that could reach across the vastness of space and tug at the very waters of Earth. The stage was set for another scientific giant, one whose insights would revolutionize physics and astronomy, providing the missing piece to the tidal enigma. It was in the quiet contemplation of an apple falling and the moon orbiting that Isaac Newton began to forge his most profound discovery. Newton's universal law of gravitation, published in his Principia Mathematica, proposed that every particle of matter in the universe attracts every other particle. This attraction, he reasoned, depended on the masses of the objects and the square of the distance between them. It was a single, elegant law for both celestial and terrestrial mechanics. Suddenly, the invisible hand pulling the ocean had a name: gravity, and the moon, our closest celestial neighbor, became the primary conductor of the tidal symphony. Newton realized that the moon's gravitational pull was not uniform across the Earth. It was strongest on the side of Earth facing the moon and weakest on the opposite side. Imagine the vast ocean as a deformable sphere of water. As the moon exerts its pull, the water responds, yielding to the force. On the side of Earth directly facing the moon, the gravitational attraction is strongest. Here, the moon literally pulls the ocean waters towards itself. This direct tug creates a bulge of water. This is one of our high tides, a visible response to the moon's immediate embrace. The Earth itself is also pulled towards the moon, but as a solid body, it moves as a whole. The water, however, is free to flow and accumulate. This explained one high tide, a clear, intuitive consequence of gravity. But the ancient observer's perplexing question remained: why the second high tide on the opposite side of the planet? This was the subtle genius of Newton's insight into differential gravity. The moon's pull acts differently across the immense diameter of the Earth. Consider the Earth's center and the side of the Earth furthest from the moon. The gravitational pull on these points is progressively weaker. The moon pulls on the solid Earth more strongly than it pulls on the water on the far side of the Earth. As the Earth's solid mass is drawn towards the moon, it effectively pulls away from the water on its far side. This leaves the water on the opposite side of Earth to lag behind, creating another bulge. It's not a push, but a leaving behind effect. So the moon creates two tidal bulges, one on the side facing it and another on the side directly opposite, due to this differential pull. As the Earth rotates through these two bulges over approximately 24 hours, any given point on its surface experiences two high tides and two low tides. The elegant symmetry of this explanation finally resolved the centuries-old mystery that had baffled ancient observers and challenged Galileo. Newton's work provided the fundamental framework for understanding the ocean's dance, revealing the moon as the celestial architect of our tides. But the moon was not alone. The sun, though vastly more massive, is also much further away. Its gravitational influence, while secondary, could not be ignored. When the sun, moon, and Earth align during new and full moons, their gravitational pulls combine. This amplifies the tidal bulges, creating the spring tides with their extreme highs and lows. Conversely, when the sun and moon are at right angles to each other during the quarter-moon phases, their pulls partially cancel out. This results in the neap tides, characterized by less extreme differences between high and low water. The cosmic dance becomes more nuanced. Newton's gravitational theory provided a unified, mathematical explanation for these observed phenomena, moving beyond mere correlation to true causation. It was a triumph of human intellect, demonstrating how abstract laws could explain the most tangible, everyday occurrences on our planet. The tides were no longer a mystery of the sea, but a testament to the universal forces that govern all matter, from the smallest pebble to the grandest galaxy. Yet, even with this profound understanding, the ocean held deeper intricacies. The simple model of a watery globe was an approximation. The real Earth has continents, ocean basins of varying depths, and coastlines that channel and amplify these gravitational forces in complex ways. These geographical features introduce friction, resonance, and delays, making tidal prediction a far more complicated endeavor than simple gravitational theory alone could describe. The dance of the tides, while fundamentally driven by gravity, is also influenced by the Earth's own shape and the dynamic nature of its waters. As we move forward, we'll explore how modern science refined Newton's insights, delving into the intricate dance of moonlight and motion that shapes our surging coastlines. Until then, keep wondering. Newton's gravitational theory provided the fundamental blueprint, but the ocean's daily rhythm held finer details. Not all high tides were equal, nor all low tides. There were subtle yet significant variations. Observers across the globe noted periods of unusually high and low tides, followed by times when the water's rise and fall was much less dramatic. These extreme tides presented a new puzzle. The Enlightenment era brought a new rigor to astronomical observations. With more precise instruments, scientists could track celestial movements with unprecedented accuracy. They meticulously charted the moon's phases, the sun's position, and the corresponding tidal ranges. Patterns emerged, hinting at a more complex celestial dance. The moon's pull was undeniably dominant, but it couldn't account for every fluctuation. There was another, subtler gravitational presence influencing Earth's waters. That presence was the sun. Though vastly more massive than the moon, its immense distance meant its gravitational influence on Earth's tides was secondary. Yet, secondary did not mean negligible. The sun's pull, when combined or contrasted with the moon's, could significantly alter the tidal bulges, creating observable effects. Scientists began to understand that the sun, too, created its own, smaller tidal bulges on Earth, much like the moon, due to its differential gravitational pull. The challenge was to integrate these two powerful yet distinct gravitational forces into a single, cohesive model that explained the observed tidal variations. This meant looking beyond the daily rhythm to the larger monthly and annual cycles, where the celestial bodies aligned in different configurations. One such configuration was a straight line, the sun, earth, and moon perfectly aligned. This celestial arrangement occurs twice a month. It happens during the new moon, when the moon is between the sun and earth, and again during the full moon, when the earth is between the sun and moon. In both these instances, the gravitational pulls of the sun and moon are working in the same direction, effectively reinforcing each other. Their combined gravitational strength creates an amplified tidal force, leading to more pronounced bulges in the ocean waters. The result is what we call spring tides. These are characterized by exceptionally high tides and unusually low tides. The term spring here does not refer to the season, but to the water springing forth or surging with greater energy. Observations over centuries confirmed this correlation. The most extreme tides consistently coincided with the new and full moon phases. It was a powerful testament to the sun's subtle, yet undeniable, role as a secondary conductor in the Earth's tidal symphony. But what happened when the sun and moon were not aligned, when their gravitational influences pulled in different directions? Twice a month during the quarter moon phases, the sun and moon are positioned at right angles to Earth, forming a celestial L shape. In this configuration, the sun's gravitational pull works against the moon's primary tidal force. They are not combining, but rather competing. The sun attempts to create its own bulges along its axis, while the moon attempts to create bulges along its own perpendicular axis. The result is a partial cancellation of forces. The sun's pull diminishes the moon's ability to create extreme tidal bulges. These are known as neap tides, characterized by less dramatic differences between high and low water. The ocean's breadth becomes shallower. The high tides are not as high and the low tides are not as low. The overall tidal range is significantly reduced. Again, centuries of meticulous observation confirmed these patterns, aligning perfectly with the quarter moon phases. But even with the sun and moon's interplay understood, one crucial element made the daily experience of tides possible: Earth's rotation. The Earth spins on its axis, completing a full rotation approximately every 24 hours, carrying every point on its surface through these tidal bulges. As a coastline rotates into a tidal bulge, it experiences a high tide. As it rotates out, it experiences a low tide. This continuous motion explains why most coastal areas experience 2 high tides and 2 low tides each day, roughly 12 hours apart. The oceans are not static basins, they are dynamic, fluid bodies, constantly responding to these shifting gravitational forces and the Earth's relentless spin. The Earth's rotation effectively distributes the moon's and sun's gravitational influence across the entire planet's watery surface. Without this rotation, a single point would remain perpetually under a high or low tide, depending on its fixed position relative to the moon. It is this daily pirouette that translates the abstract celestial mechanics into the tangible, observable rhythm of our oceans. The complex interplay of the moon, the sun, and Earth's rotation painted a far more complete and accurate picture of tidal phenomena. This refined understanding allowed scientists to predict tidal variations with much greater accuracy, a critical development for navigation and coastal communities. The Enlightenment era's commitment to precise measurement and mathematical modeling had truly illuminated the cosmic dance of gravity. Yet, even with these profound insights, the real-world oceans presented further complexities. Earth's geography was not a uniform sphere. Continents, ocean basins of varying depths, and narrow channels all played a role, channeling and modifying these gravitational forces. The next step in this scientific journey would be to understand how these geographical features fine-tuned the gravitational symphony, creating the unique tidal patterns of every coastline. The elegant theories of Newton, refined with the sun's influence, offered a profound understanding of tidal forces. Yet, the real-world ocean, with its complex geography, refused to conform to a perfectly smooth, watery globe. Coastal observations revealed inconsistencies. Tides in one bay might be dramatically higher than in an adjacent, seemingly similar, inlet. The timing, too, varied greatly from predicted gravitational models. The simple equilibrium theory, which assumed water instantly responded to gravitational pulls, was a powerful start, but it treated the ocean as a static response, not a dynamic, moving body. Scientists realized the solid landmasses, the varying depths of ocean basins, and the very inertia of the water itself played critical roles. The Earth's rotation added another layer of complexity. This led to a shift in thinking from a static view to a dynamic one. The tides were not just bulges, they were vast, rhythmic waves propagating through the global ocean, interacting with every obstacle. The dynamic theory of tides emerged. It considered the actual movement of water, its friction against the seabed, and the way ocean basins could amplify or diminish tidal energy. Imagine the tidal bulges as immense, shallow waves driven by the moon and sun, but then profoundly shaped by the Earth's physical structure. Continents blocked their free movement. These waves could not simply follow the moon's direct pull. They were forced to slosh back and forth within the confines of ocean basins, reflecting off continental shelves. The Coriolis effect, a force resulting from Earth's rotation, became crucial. It deflected moving water, causing tidal currents to swirl in vast, circular patterns in open oceans. This meant that in many places, high tide might occur long after the moon had passed overhead. The ocean's response was a delayed, intricate dance. Local geography became the grand amplifier or dampener. Narrowing bays and estuaries could funnel incoming tidal waves, dramatically increasing their height. Conversely, broad, shallow continental shelves could dissipate tidal energy, leading to smaller tidal ranges in some areas. The depth of the ocean basin also mattered. Deeper water allowed tidal waves to travel faster, while shallower areas slowed them down, affecting their timing and amplitude. Friction with the seabed, particularly in shallow coastal waters, also played a role, absorbing energy and influencing the speed and shape of the tidal wave. These factors meant that tidal patterns were unique to almost every coastline, a complex fingerprint of celestial mechanics interacting with Earth's physical form. One of the most powerful concepts uncovered was resonance. Just as a pendulum has a natural swing, ocean basins have a natural period of oscillation for water sloshing back and forth. If the period of the incoming tidal wave closely matched the natural oscillation period of a bay or basin, the tides could be dramatically amplified. This was like pushing a swing at just the right moment, making it go higher and higher. Small gravitational forces could build into immense tidal ranges. Identifying these resonant basins became a key focus for oceanographers, explaining some of the most extreme tidal phenomena on Earth. The challenge was to accurately model these complex interactions, combining gravitational forces with the physics of fluid dynamics and specific geographical data. Nowhere is this amplification more dramatically displayed than in the Bay of Fundy, nestled between New Brunswick and Nova Scotia in Canada. Here, the bay's unique funnel shape, combined with its length and depth, creates a nearly perfect resonance with the incoming tidal wave from the Atlantic Ocean. The result is astonishing. The Bay of Fundy experiences the highest tides in the world, with differences between high and low water reaching over 16 meters, 50 feet. Scientists meticulously studied this natural laboratory, deploying instruments to measure current velocities, water levels, and seabed topography. Their findings confirmed the power of resonance and geographical channeling, transforming a subtle gravitational tug into a monumental surge of water. Another powerful manifestation of dynamic tides is the tidal bore, a rare and often spectacular phenomenon found in certain rivers. When a very high tide enters a river that is shallow, narrows significantly, and has a strong outgoing current, the incoming tide can form a breaking wave. This wave or bore travels upstream, sometimes for many miles, a wall of water often several feet high, pushing against the river's flow. Famous examples include the Kayentang River in China, known for its immense bore, and the Severn Bore in England, which draws surfers and scientists alike. Studying bores provides insights into extreme fluid dynamics, the interaction of river and ocean, and the powerful, sometimes dangerous, energy of surging coastlines. Beyond vertical rise and fall, tides create powerful horizontal movements of water, tidal currents. These currents are vital for navigation and marine ecosystems. The Coriolis effect, combined with the shape of ocean basins, causes these currents to rotate in open water, creating elliptical paths over a tidal cycle. In narrow channels and straits, these currents are often amplified, rushing through constricted passages with considerable speed and force. Accurately predicting these currents requires sophisticated models that account for depth, seabed friction, and the complex interplay of gravitational and inertial forces. The development of advanced numerical models and supercomputers allowed scientists to simulate these intricate movements with increasing precision. This advanced understanding led to the creation of detailed tidal current charts, essential tools for maritime activities worldwide. Shipping, fishing, search and rescue operations, and coastal engineering projects all rely heavily on accurate predictions of both tidal heights and currents. From ancient memorized patterns to complex computer models, the journey to understand the dynamic dance of coastlines was one of continuous refinement and technological progress. Each new observation, each model, brought humanity closer to truly comprehending how the moon's quiet pull orchestrated the powerful, often hidden, movements of our oceans. As we grasp these dynamic forces, we begin to see not just the challenge, but the immense potential. This understanding now guides us toward harnessing the very power of the tides, a story we will explore next. The intricate dance of coastlines had been deciphered, revealing not only the ocean's power but also its profound predictability. This steady rhythm, unlike the fickle wind or intermittent sun, held a compelling promise. For centuries, humanity had observed this colossal energy, sometimes with awe, sometimes with trepidation. Now, the question shifted. Could this ancient pulse be tamed, its ceaseless motion put to work? The late 19th and early 20th centuries saw the first serious engineering proposals. Minds turned from simply predicting tides to envisioning structures that could capture their immense, daily surge. Engineers recognized the sheer volume of water moving with each tide. If a river could turn a mill, surely an entire ocean's ebb and flow held far greater potential. The primary challenge was scale. Harnessing such a colossal, diffuse force required monumental constructions, far beyond anything previously attempted for energy generation from water. Early concepts involved creating large impoundments. Water would flow in at high tide, be trapped, and then released through turbines as the tide receded. This was a direct application of hydroelectric principles, but adapted for the unique bidirectional flow of tidal waters. The engineering hurdles were immense. The dream was of clean, renewable energy, free from fossil fuels, powered by the moon's unwavering gravitational embrace. It was an ambitious vision for a new era. The predictability of tides was its greatest asset. Unlike solar or wind power, the timing and magnitude of tidal energy were known years in advance, offering stable baseload power. This steady rhythm promised a constant, reliable source of electricity, a compelling solution to a world increasingly reliant on energy, yet seeking sustainable paths. The mid-20th century saw this vision take concrete form in France. The Rance estuary, with its significant tidal range, was chosen as a pioneering site. Here, the French embarked on an audacious project, the construction of the La Rance tidal power station, a colossal barrage spanning the estuary. Completed in 1966, La Rance was the world's first large-scale tidal power plant. it stood as a testament to human ingenuity and perseverance. The barrage worked by creating a reservoir. At high tide, sluice gates opened, allowing water to fill the basin behind the dam. As the tide turned and the ocean level dropped, the trapped water was released through 24 large turbines, generating electricity. These reversible bulb turbines were a marvel of engineering, capable of generating power from water flowing in both directions, maximizing energy capture. Lorentz demonstrated the viability of tidal barrages, proving that the ocean's rhythmic breath could indeed be converted into electrical power. However, barrages also presented environmental challenges. They altered estuary ecosystems, affecting fish migration and sediment flow. The immense upfront cost of construction and the significant ecological footprint limited their widespread adoption, despite their energy potential. While Lorentz continued to operate effectively, scientists and engineers began exploring alternative, less invasive methods to tap into tidal power. The focus shifted from damming entire estuaries to harnessing the energy of tidal currents directly, much like wind turbines capture wind. This new approach centered on tidal stream generators. These devices would be placed in areas with strong, predictable tidal flows. Imagine large, robust turbines anchored to the seabed, their blades silently turning with the ebb and flow of underwater currents. These underwater turbines convert the kinetic energy of moving water into electricity, similar to how a windmill works, but in a denser medium. The density of water means that even relatively slow tidal currents can carry immense power, requiring smaller blades than air turbines for equivalent output. Early prototypes were deployed in test sites with strong currents, like the European Marine Energy Centre, (EMEC), in Scotland. Engineers faced formidable challenges: corrosion in saltwater, biofouling, and the immense forces of ocean currents demanding extremely durable designs. Developing robust materials and maintenance strategies for equipment operating miles offshore, deep underwater, became a critical research frontier. Despite the difficulties, successful deployments proved the concept viable. Tidal stream technology offered a path to clean energy with less ecological disruption than barrages. These underwater farms could be scaled, placed in areas where strong currents naturally occur, minimizing impact on sensitive coastal habitats. Around the world, experimental and commercial tidal energy projects began to emerge. Canada, the UK, and South Korea became key players. In the Bay of Fundy, where the tides are highest, innovative projects explored both barrage and in-stream turbine designs, leveraging its unique geography. The Minas Passage in Nova Scotia, a narrow strait within the Bay of Fundy, became a focus for advanced turbine testing due to its extreme currents. These projects represented a significant step forward, moving from theoretical possibility to tangible, electricity-generating reality. The potential of tidal power is immense. Estimates suggest it could provide a significant portion of global electricity needs, especially for coastal nations. As a constantly renewing, predictable energy source, it offers a crucial piece in the complex puzzle of transitioning to a sustainable future. However, challenges remain: high capital costs, the harsh marine environment, and the need for robust grid integration. Research continues to refine the technology. The ocean's rhythmic breath, once a mystery, then a force to be predicted, is now becoming a partner in our energy future. Its pulse, a silent, powerful contributor. This journey from ancient observation to modern engineering highlights humanity's persistent quest to understand and responsibly interact with our planet's forces. As we consider the future, the question becomes: How will we integrate this silent power into a global tapestry of sustainable energy, and what new discoveries will emerge from its deep, rhythmic flow? We have journeyed from ancient shores to modern engineering, unraveling the moon's quiet pull. Yet, the story of tides extends beyond the ocean's surface, reaching into the deep mechanics of our solar system. The very act of the ocean rising and falling, driven by gravitational forces, creates a subtle but profound effect: tidal friction. It's an invisible drag, a constant brake on Earth's rotation. Imagine the vast masses of water pulled into bulges moving against the solid seabed and continental shelves. This movement generates friction, a resistance to the Earth's spin. This friction acts like a gentle, persistent hand, slowing down our planet's rotation, millisecond by millisecond, over immense stretches of geological time. Scientists have meticulously studied ancient fossil corals and rhythmic rock formations. These records reveal that Earth's day was much shorter billions of years ago. For example, 400 million years ago, a year contained about 400 days, meaning each day was only about 21 hours long. Tidal friction has stretched our days. The energy lost from Earth's slowing rotation doesn't simply vanish. It is transferred, a fundamental principle of physics, into the moon's orbital motion. This subtle energy exchange is a continuous, unseen process, a testament to the elegant interconnectedness of celestial mechanics. The Earth's rotation continues to slow, albeit imperceptibly in our lifetimes. Every century, our day lengthens by roughly 2–3 milliseconds. This tiny increment, accumulated over eons, paints a picture of a planet whose very spin is being gently reshaped by its closest companion. As Earth loses rotational energy, the Moon gains orbital energy. This increase in energy has a remarkable consequence for our lunar neighbor. The Moon is slowly but surely drifting away from us, a fact confirmed by precise laser ranging experiments bouncing light off reflectors left by Apollo missions. Each year, the Moon moves approximately 3–8 centimeters further from Earth. It's a tiny distance, but over geological timescales, it adds up significantly. Billions of years ago, the Moon was much closer, appearing far larger in our sky and exerting even more powerful tidal forces on our young planet. This recession of the Moon means that future solar eclipses will eventually become less frequent and less dramatic as the Moon's apparent size diminishes. The Earth-Moon system is not static. It is a dynamic, evolving dance, choreographed by the universal law of gravity and its subtle, long-term effects. This continuous interaction ensures that the gravitational overture plays on, shaping our world in ways we often overlook. It highlights the patience required in scientific inquiry, where effects that seem minuscule in a human lifetime become monumental over cosmic spans. The Moon's gentle retreat is a reminder that even the most familiar celestial relationships are in constant, slow flux, evolving with time. Our understanding of tides thus extends from the ocean's edge to the very destiny of our planetary system, a profound realization. This gravitational dance leads to another fascinating phenomenon: tidal locking. It's a state where one celestial body always shows the same face to another. Our Moon is tidally locked to Earth. That's why we always see the same lunar face, a constant companion in our night sky. This locking is the ultimate consequence of tidal forces over billions of years, slowly slowing a body's rotation until it matches its orbital period. It's a common occurrence in our solar system. Most of the large moons of Jupiter and Saturn are tidally locked to their gas giant parents. Pluto and its largest moon, Charon, are mutually tidally locked, each forever presenting the same face to the other, locked in a perpetual embrace. In the distant future, billions of years from now, Earth itself will likely become tidally locked to the moon if the sun doesn't engulf us first. This means one side of Earth would perpetually face the moon and the other would always face away, creating vastly different environments. Such a world would be profoundly different, a testament to the long-term, transformative power of gravitational interactions. Tidal locking is a natural endpoint for many celestial pairs, a stable configuration achieved after eons of gravitational give and take. It shows how even the most subtle forces, given enough time, can fundamentally reshape the spin and orbital dynamics of worlds. The story of tides, therefore, is not just about our oceans, but a timeless gravitational overture playing across the cosmos. From the quiet pull of the moon on Earth's waters to the intricate dance of binary stars and exoplanets, gravity orchestrates all movement. It is a force both familiar and mysterious, explaining why apples fall and why galaxies spiral, connecting the mundane to the magnificent. Our journey has illuminated how observation and patient inquiry reveal these profound connections, layer by careful layer. The science of tides, once a source of myth, then a puzzle for great minds, is now a window into the elegant mechanics of our universe. It inspires us to continue asking questions, to look closer, to seek the hidden patterns in the grand tapestry of existence. For every answer we find, new questions emerge, leading us deeper into the subtle complexities of our cosmic home. The rhythmic breath of the ocean, driven by moonlight and motion, is a constant reminder of this ongoing scientific quest. It is a dance of incredible power and subtle grace, a symphony of forces that continue to shape our world and inspire our wonder. And so, as the moon climbs high, casting its silvery light upon the tides, we are left with a deeper appreciation for this timeless gravitational tune. Sleep well and keep watching the skies.